Hi, my name is Anshu and welcome to my channel Bottleneck. This is the Data Structures and Algorithms series. In this series, we will be implementing algorithms and data structures using Scala functional programming approach. This video is part 3 for Dijkstra's shortest path algorithm. In part 2, we had implemented the weighted graph. In part 1, we understood what a shortest path algorithm is and how it will traverse and how it will boil down to the shortest path from a starting node. Now in this video we will be implementing couple of helper methods to for the shortest path algorithm to make it happen. Now I took the liberty to implement this graph, so this is something similar of what we see here, A to B, A to C. So if you see A to B, the weight is 4 and A to C the weight is 3. So here A to B weight is 4, A to C weight is 3. Similar for B to C is weight is 2 and B to E weight is 1. So B to C weight is 2, B to E weight is 1. So you can follow along and you can also create the similar graph like this. So this is a weighted graph. Now to start with Dijkstra's shortest path algorithm, we need a placeholder to hold the route and the weights, the accumulated weights. So we create a case class and this will be the path that we will need, and this will give us the route. Basically it is going to be sequence of all nodes and it is going to give us the weight, which is going to be end. So initially let's initialize it as 0 and let's initialize this as empty value. So initially this is, we can use it as a value because it's a case class. That's the beauty of a case class. Now first method that we will require is add a path to the sequence of the paths. So our objective is to return something like sequence of paths. So each path that we see here will hold a unique route to from source to the destination with the accumulated weight. So how it is going to work? Def add path to route. Sorry, I need to use it. Add path to route, and it will be of type V, which will require first element as path, which is basically sequence of path, which is of type V. Second element would be the path itself of type V. Third element is the accumulated value. It is again going to be sequence of path V. So in every iteration we have to check for the visited. Also we need to append if those nodes are not visited. So because this accumulator is initially going to be empty, so we can mark this as empty, so we can be rest assured that it is going to be empty. Now we will require this graph every time, so we will declare it as implicit so that we don't have to worry about this graph anymore. Okay, and it is going to return a sequence of V. Perfect. Sequence of path of V, because we are returning the path. Okay, so how we are going to implement this? We will use a pattern match on the path where first case is always going to be nil, because at one point in time it's definitely going to be nil. So what will happen when it is going to be nil? When entire path is traversed, then it will check if the accumulator dot map underscore dot route dot last. So it will check whether all the last element, so sequence of, because we need to know the destination, right? So if C is visited once, then if C is visited twice, then it will check the destinations. For example, if I go here, so first A, C, the weight is 3. Now there will be another route A, B, C. So the weight will be 4 plus 2, 6. So in this case, C is common destination, but weight is less here. So we have to drop this and keep this. So to do that, we need to check if it contains the p dot route dot last. If so, then it will return the accumulator, else it is just going to add this value. It means it doesn't exist as of now. Now the second pattern would be a pattern will split the head and the rest. Now we are going to check if x dot route dot last equals to p dot route dot last. So if the last node, say we are comparing here C, so here the last node would be C, here the last node would be C. So it is comparing. If it is C, then what we are going to do, we are going to check if x dot weight is less than p dot weight. If so, if that is the case, then add to path, and it is going to be access comma p comma acc, and we are going to append x. We are not going to do anything because already we have something which has a less weight. So add to path, and then here, if not, if our new path has a less weight, so story ends here. We will append everything, and we will also add p to this, so there is no more iteration required. Okay, it is something is it missing? Yeah, we have to pass p as well. Okay, so now this structure looks fine. Third case, so this is done. So now we have another case. So because what is this for? So here we had looked into if route x dot route dot last equals to p dot route dot last. But what if this is not true? Then it will jump to this case. So this will basically traverse to the next value that we have, access comma p comma acc, and it's going to add x. So if you see, we are getting this third the second input parameter as implicit, so it is automatically being called because we have declared implicit, so we don't have to pass in that value every time. So this is the add to route method, and let's add one more method. So this will be update route or add new path. So we also need to check update route. It will be also type v. These are all helper methods, so we are going to pass all the neighbor. So this is going to be one neighbor at a time that is being added, and we have the path which is going to be sequence of path of v, and it also has the accumulator path which will be again sequence of type path of v. Again, we also need a graph here, so it's going to be implicit graph of type v, and it's going to return again a path, a sequence of paths. So let's implement this. Same thing here, we have a pattern match for path, and we will add each element at a time. So it's going to be case nil. What happens if that neighbor or the entire traversal is done? So it is going to return my accumulated value. If not, then what we are going to do? We are going to do a pattern match, split the head and the rest, and it is going to check if graph dot neighbors, and we are going to pass here x dot route dot last. So we are going to see that the element, before adding that neighbor to our route, we need to check whether it is actually a neighbor. A node is actually a neighbor. So it will check neighbor. If true, then we have to create a var new accumulated path, which will be basically add paths to route. Here first is ACC path that we are going to pass, and second element is going to be path of x dot route appending to the new value that we have, and that is neighbor dot destination, and we need the second element x dot weight plus neighbor dot weight. Okay, now we are going to return this method. So it's going to be a tail recursion neighbor comma access comma new accumulated path. Okay, now what if it doesn't contain our neighbor? So we will implement this pattern again, and it's going to just return update route neighbor comma access comma accumulated path. Okay, so we have implemented two helper methods which we will be leveraging for our shortest path algorithm. There is further to go, and let's see you in the next video. If you enjoyed this video, please like and subscribe. Do not forget to press on bell icon to look onto my further updates, and link to the code will be provided in the description as a link to my GitHub repository. Thank you.